Hi, everyone, again, and welcome. Thanks for joining us today as we talk about constraining language runtimes for deterministic execution. My name is Kelly, and I'll be your host for today. And before we get started, just going to cover a couple of housekeeping items. If you have any questions, we would love to hear them. We'll have a Q&A session at the end of our presentation with our speaker, Chad, here. So go ahead and add your questions to the Q&A feature below, and we'll add them to our queue. And second, we are recording today's session, and we'll send you a copy of it either later today or early tomorrow, so you can revisit and share with your friends and colleagues. And lastly, if you have not heard the news, Temporal is hosting our annual replay conference in Seattle, and that is September 12th to the 14th. So if you are not familiar with this conference, it's a conference dedicated to the platforms, practices, and trends in backend software engineering. And this year we have 3 full days packed with workshops, talks, and topical discussions with folks from the Temporal team, along with innovators from the broader community. So we would love to see you there. You can check out more information about replay at temporal.io/replay. All right, so now let's jump into even more exciting things. I'm thrilled to introduce today's speaker, Chad Retz. Chad is a software engineer here at Temporal and works on the SDK team and helps develop SDKs in many languages. And in addition to working on existing SDKs, Chad has also developed the Temporal Python and .NET SDKs. You also, if you're on the community Slack channel, you've probably worked with Chad a lot and recognize his name at least. So I'm excited to have Chad here. He has a fantastic presentation prepared for you all. So at this point, I'm going to hand it over to you, Chad.
Hello, everybody. Thank you very much, Kelly. So today we are going to talk about limiting language runtimes to be deterministic. And so it's not necessarily how you as the developer will be able to do this, but more about all the struggles and approaches we at Temporal have to try and do this for you. And there's a lot of content. I'll kind of blow through it, but we'll have some questions at the end. So what are we going to go over? So first, we're going to discuss basically the common types of deterministic violations that happen in just about any language. They're not really unique to any specific language. And then we're going to discuss some of the challenges and approaches we take in the different runtimes. So Go, JVM, Node.js, Python.NET. And we're going to grade each approach we take to try and keep people in this deterministic box by how hard it is to implement and use and how well it works. And this grading can kind of help give a guide on whether it's even worth doing. And then we have some extra topics around AI and WASM and fuzzing and stuff if there's some time. So without more, let's get started. So what is deterministic execution as far as Temporal is concerned? So not activities, just workflows have to be deterministic. They have to be deterministic just so that they can essentially replay and resume on other workers without loss. Now, if you go to like Wikipedia or something like that, you read the definition of determinism. It's that the same code paths and the same effects have to happen for the same input. At Temporal, it's a little more nuanced and a little more vague, but it's essentially the same commands have to happen for the same input. So when a workflow runs, it essentially is triggered by events from the server, and it produces commands back to the server. And we check those commands when we replay, such as during a replayer or when a workflow goes to another worker. When we replay, we check that the commands are the same as they were when you originally ran. And if they mismatch, that's when we what we consider non-determinism. But not every little part of a command is checked, So, if you change a timer or a sleep from 5 seconds to 10 seconds, no problem. We don't really check it that detail, or like some of the activity input. But if you add a timer or change the entire activity that's being called or something like that, that is non-determinism error, and we will catch it. So what are the ways that these are violated? What are the common ones? Right? And they're pretty straightforward. There's only 3 of them. So the first common way is calling non-deterministic things. So if you're asking for the current time or asking for something random, that's obviously non-deterministic because it can change from run to run. If you're using disk IO or other things that have external access, that can also be non-deterministic. It may not work the second time, if you will. Threading is also inherently non-deterministic most of the time because of the way these schedulers work. And a lot of times, iteration of hash maps and hash sets tend to be non-deterministic, or even if they're deterministic within themselves, they're non-deterministic if you make an alteration. At least a lot of times they're not predictable. And different languages have different approaches to this. We'll discuss it later. So how do we solve for illegal calls? Well, we can emulate the calls. We can change what the system considers the current time to what the workflow considers the current time. The problem is that developers have certain expectations around that. So they're probably not used to maybe it always being UTC or not being monotonic or something like that. We can use static analysis. So static analysis is a lot of times the best approach, especially in typed languages or in dynamic languages where you use type hinting. And then we could also prevent them. So we could basically say, you tried to ask for the current time, that's not allowed. Some languages allow this more than others. Unfortunately, this only catches it at runtime, so it's not always the best approach. Another way that you can violate non-determinism is shared state mutation. Pick your language. They all have globals and statics, and a lot of times they allow them to be mutated from inside of a workflow, which means that you can easily take a different code path based on mutations that are external to the workflow. So ideally, we want to be isolated. And a lot of people are like, oh, well, I have read-only static information. Is it that big a deal to access externally? A lot of times, if it's not constant and hard-coded, it can be because different workers may have different configuration values and such. So we discourage that as well. The best approach is to prevent this, sandboxing it. Static analyzers don't work as well here because it is hard to tell deterministic from non-deterministic global variable access. It's a lot of times intent-based. And then there's also runtime interception, but most languages don't allow you to intercept reads and writes to global variables. And then there's the third approach, the third violation of determinism, and that's code changes. And this one is the hardest. And this one you can't really build that many automated tools for in today without using AI assistance or something. So for the basically you can if a workflow replays on a newer piece of code that takes a different path than an older piece of code, then it can look non-deterministic if it takes different code path. We're not going to really concern ourselves with solving that because that is a very hard problem to solve and there's no real good solutions. What we're going to concern ourselves with is just so long that the workflow author, it's obvious that if they make a change, that change could result in a non-determinism. So anything hidden in the runtime that could reorder coroutines, not okay. So with those basic three violations known, let's get into the different languages and how we can try and keep that from happening. And these are all temporal researched ideas and approaches. Some of them are vetted more than others, but they're all interesting to discuss anyways. So first, let's talk about Go. Very, very popular SDK, but very inflexible. So Go, you can't use any of the concurrencies. Any selects, any Go routines, any of that, all of it is non-deterministic because their scheduler is non-deterministic. And even if you did use single buffered channels in a deterministic way, we can't really guarantee that you will always use them in a non-deterministic way. So all concurrency constructs are out. Map iteration cannot be done, or it should not be done. Ranging over a map in Go is not only non-deterministic, it's inherently so much so that the Go authors put in randomization so that you wouldn't rely on the order of iteration of a map. And then, of course, the standard library stuff, can't do time, can't do unseeded random, things like that. And the way that Go works, we can't really do much to the language at runtime, or really at compile time. It's very inflexible. It does this on purpose. It likes to be opinionated, which is why a lot of people like Go, but it's hard for us to sandbox it and prevent certain things at runtime. So we have written a static analyzer, but that's about it. So the first approach in Go to preventing non-determinism, static analyzer. So we wrote a static analyzer. It will check for bad calls or using async constructs. It doesn't really check for shared state mutation. That's a really hard one to check because a lot of times people use shared state deterministically, but we can improve it. But overall, it wasn't that hard to write, and it's actually reasonably effective. So, grade of B all around. And this is out there today. Strongly recommend that people use it. So there's also a possibility of writing an interpreter, and there interpreters exist for Go, the Yagi one. There's an SSA one inside of Go's auth library there that both of them are not full featured. And we'd have to write our own full featured one. This would be great. It is very challenging. It's easier to do in Go than it is in other languages, but it's still incredibly challenging and difficult to maintain and may not be worth it for a lot of users. Not really concerned about the performance, just that it is difficult to maintain and to get all the Go constructs right. Even though it's easier in other languages, it's still fairly difficult. So this is a D on difficulties. Even though it would work pretty well, it is a difficult challenge. There's another option, and I toyed around with the proof of concept of this, of transpiling at compile time. So Go does have code generation, and it actually lets you add a custom compiler kind of at build time. But a lot of people don't like their Go build to be overridden anyways, but this could work. But it is a lot of work to transpile all of that, to alter the code for all of the deterministic, non-deterministic constructs to make them deterministic, yet still preserve debugging and line numbers and all that such. So while this is technically possible, it is difficult. But if you did do it, it would be a great approach. There would be no getting out of it. We could sandbox it all at compile time. So it's a possibility, but it's tough to do. And then there's a few, besides those three approaches, there's a few other approaches that are mostly not okay. So Temporal can't reasonably maintain a fork of Go. That's it moves too fast, and people wouldn't like it. People like to be in their own runtime, especially their activities run there. So forking Go is a no-go, if you will, so to speak. Now we could also contribute a deterministic scheduler inside of the Go runtime. And Max, our CEO, actually opened an issue to this effect a few years ago that basically said, hey, can we have a deterministic form of this in the runtime? And the Go maintainers are like, look, your use case is kind of cool, fairly unique, but that's just not something that we're willing to do. And they're pretty opinionated, so this just won't happen. And then there are other approaches with runtime tracing. You can monkey patch some of the runtime, or you can use some external tracing tools, eBPF and such, but none of them are very foolproof. And the problem is that they alter the whole runtime, not just the workflow side. So that's a bad thing. So these approaches are no good. We'll get to the, at the end of the talk, we'll get to the verdict of all the different languages and what we're thinking about implementing. But so there you have it for Go. That about sums it up. And that's probably the one that I dug into the most. But we also have others like the JVM. So the JVM, there's a lot of flexibility in running the JVM, sometimes to a fault, but it's moving these days. It's moving very fast. Ever since it left Sun, it just started moving really fast. And so what approaches can we take to prevent, well, first of all, what are the challenges on the JVM that exist for people wanting to write deterministic code? So obviously all the common ones, the standard libraries, the time, random, IO, things like that. The other problem that exists is that unlike most of our other runtimes, it is very common to use languages other than Java on the JVM, Kotlin, Scala, Clojure, whatever. So we have to make sure that our approaches apply to them. We can't just use the popular language of the runtime. And the fact that it has bytecode and it's instrumentable helps, but we have to be cognizant of other code running inside of that same JVM. We can't just take over the JVM for our purposes unless the user be willing to, but most users for ease of use don't necessarily want to. So most obvious approach is static analysis. Now we don't have a static analyzer for Java, but I think we're going to get there. So there are some static analyzers out there. Checkstyle is the popular one, but it's mostly only Java. But they did all the hard work of going through the JDK, go through all the standard runtime, and marking which calls are or are not deterministic so that we can use those transitively. But we can't really use that annotation because it is much more strict than temporal's definition. It doesn't even, like, if you construct an object, it's considered non-deterministic, which is just silly as far as temporal is concerned. So we can't even use that. We would have to go annotate the JDK ourselves. That's fine. We can get most of it, even if we don't get it all 100% accurate. So that's totally doable. There are some other tools besides check style, like SymGrep and others that can help us here. But either way, a lot of the work would be on us to mark what we consider non-deterministic and then transitively check. And the benefit is that workflows are clearly marked. So it's not like we're going to get a bunch of false positives for code not called from workflows. And we can transitively determine. Of course, like every static analyzer, you can use reflection to cheat it. Same with Go, though. We can't really stop you from accessing and using static fields because a lot of times it's done deterministically. But this is, in general, bees all around, a great approach. It is not that difficult to write, and it is fairly effective. So this is a good approach. Now, to make an interpreter or to sandbox code in the JVM, there are lots of them out there. There are metacircular interpreters written in Java that interpret the Java IR, and it works just fine. But the Java IR is moving faster than most of those move. In fact, the only one that I think is probably a decent interpreter is actually the Graal one itself, the one that Oracle writes itself. Otherwise, the rest of them are falling a little behind on class files, the JITES and such. So we could probably use that. There are a couple of deterministic runtimes out there, like this Quarter one is written for blockchain smart contracts. It's just not generic enough for what temporal will need. There's also this concept of JVM-TI, which is basically a native interface. It's like JNI for debuggers. It allows you to literally step through code, but as soon as you do that, you throw all performance out the window, and it's not always supported on all JDKs, so it's not really the best approach either. As far as threading goes, we couldn't emulate threading. We just have to disallow it. There are too many thread-based calls and too many confusions on when threads run that we couldn't easily make a deterministic threading. Now, we could talk about virtual threading in Project Loom and things like that separately, but in general, it's not, we can't emulate the threading reasonably inside of a sandbox anyway. So, and then there's, of course, the performance issue that doesn't apply to Go as much as it applies to the JVM, just because the standard runtime library is so much larger in the JVM and goes through so many steps, and it's hard to cross the boundary of having it like half JIT host side and half sandbox side. So, in general, this gets a lower difficulty grade just because it's hard to do. But if we did do it, it would work well, but it's harder to do. And then you have runtime tracing. So, and I've written, anybody that's done hardcore work on the JVM has written their share of agents that instrument the bytecode, you know, using tools out there. The problem is that at bytecode instrumentation time, you don't really know if it's code that's going to be transitively called by a piece of workflow code. So we essentially would have to inject hooks into everywhere people may be using thread or calling time and things, and that can have a performance hit. Technically, you can use like OSGI or custom class loaders, but if anybody that has tried to do that before knows, it's hard to keep people in their class loader sandbox. It is very easy, for instance, for reflection to use the system class loader, and loading multiple of the same class on different class loaders can cause all kinds of confusions with different versions of the JVM. So in general, while you can do runtime instrumenting and runtime tracing to catch illegal calls and to catch mutable state to maybe make it thread local to the workflow, it is very hard to do, but it is doable if the workflow authors would be willing to only use that JVM for running workflows. So, you know, leave your activities and all the rest of your JVM work elsewhere. We try not to do that at Temporal because people like to run inside of the process where they do other work. So it is hard to do, but if people were willing to do it, it is reasonably effective to put to instrument the bytecode and put prevention hooks in there. So that's basically it for the JVM, and we'll get to the verdicts again later. But now let's move on to from one of the hardest to one of the easiest, Node.js. So obviously, JS was built to be sandboxed. You know, your browser is, and V8 does a great job at exposing all ways that we might want to sandbox. So that's what we use. If you are using the TypeScript SDK today, you have the best guardrails against non-determinism of any of our languages by far. It's hard to cheat, though it technically can be done. It's hard to make a mistake. We control all the promises. The standard runtime library is small. People in JS are used to having no threads and just using coroutines and promises, so no problems there. We bundle for you, which means that we can shake and check things at workflow registration time or at build time if you want to bundle ahead of time. There are some memory concerns with starting a separate bundle inside of a V8 context each time, but we can alleviate those since we control that, very similar to how V8 caching might do it across your browser tabs or such. So even though this was a little bit hard to write and can be a little bit hard to use due to the bundling, this gets an A for difficulty because for the most part, people don't have to think about it. And it gets an absolute A for effectiveness. It is the most effective non-determinism prevention tool Temporal has. And if all of the languages could do this, that would be great. But they all can't. But there's one other thing that static analysis could help with in Node.js. We require queries and workflow update validators. Update's a new thing coming out. It's gonna be awesome. We require queries and update validators to be side effect free. And that's where a static analyzer can help. We aren't really going to isolate those in separate V8 contexts because it's just unreasonable for how frequently they run. So it is possible that we might write a static analyzer for JS and for the TypeScript SDK just to keep you from making side effects inside your queries that could cause some issues. But other than that, the Sandbox mostly solves it. So this isn't that hard, but it's questionable on how much benefit it has only for queries and update validators. So moving from Node.js, we now have Python. So Python is super flexible and it has an interpreter built in, but it is so flexible, people use it in so many ways that it is incredibly hard to constrain. And you don't really want to constrain it. The whole reason why people might use Python is because of its unconstrained nature. So let's go over some of the difficulties with it. So Python has this coroutine construct now built in called async IO. And we leverage that to its fullest to create a completely deterministic event loop, which is awesome. And it means that people can use async await deterministically inside of Python, which is very nice. There are some aspects of async IO, like everything, like the actual IO part that we disallow. They also allow you to do things based on deadlines. So you could tell it to call later based on a duration, and we'll turn that into a workflow timer, no problem. But if you tell it to call at a certain time, that's unreasonable for Temporal to do because current time is not a deterministic facet. And we could subtract it from what workflow knows is current time, but we can't do it predictably from the user perspective. So we disable those parts in the async IO. And Python, since it's an interpreter, there's lots of sandboxes out there, but none of them are very good. And Python will tell you, well, sorry, Python just cannot be securely sandboxed. But we don't care if it can be securely sandboxed. We just want it to be sandboxed insecurely just for some isolation. Well, they do have evaluators and interpreters that you can, the CPython and the standard library has an eval and an exec, and we actually leverage that. But we had to build a whole bunch of complex machinations around it in order to isolate state. We had to do our own custom importer. We had to do our own little proxy objects to restrict access to certain pieces of the standard library that are non-deterministic. We reload a lot of the modules on run, or we ask the user to pass them through, which kind of harms the user's ease of writing. But otherwise, it's easy to tell when we're doing bad things in Python. And of course, Python, due to its performance and other reasons, has a lot of extensions written in C. We just can't do anything about that. We have to ask that those C libraries be deterministic because we can't reasonably sandbox those. So the primary approach is using the interpreter as a sandbox and tracing. This is what we do today. So we wrote a custom interpreter that's reasonably memory efficient because it passes through a lot of modules. And it restricts calls like datetime.now and things like that. The problem is that there are certain little subtle Python bugs when you proxy existing objects for certain internal calls that CPython makes. we can't intercept them all. So there are a couple of known issues that are in the Python README. We do have to maintain our own curated list of standard library calls that are non-deterministic, and we have to ask users to pass through their own libraries as imports, because it is not very performant to completely reload every module on every single workflow. So ones that users know are deterministic, or just using them in deterministic ways, such as importing an activity name or importing input and output, data classes, we have to ask that they're passed through just to preserve performance. So that's where the difficulty of C comes in, is it was hard to write, but it is also puts a little bit of a burden on users. However, it's reasonably effective. You set a global variable inside of your workflow file or inside your workflow module, it's not going to infect the other workflows. So that's a very good thing. It was a very hard trade-off for us to decide, burdening the user with this sandbox and the concept of pass-through modules and stuff. Was it really worth it to get global isolation? So far, it has been. Hopefully, it'll stay that way. And then there's an approach we plan on taking, just haven't done yet, a static analyzer. This, we basically need to do it in every language. There's so many wins and so few losses. In this case, it is most Python is reasonably statically analyzable, even when not used with type nets. Now, some of it isn't as much, especially especially when you start going in and out of dictionaries and stuff. But in general, it is not that difficult to write, and it's fairly effective for us to prevent, at some type of build time step that you would have to call manually, to prevent bad calls. We can do it, and it's definitely something on our radar. So that basically wraps up. Sandbox it. We need to statically analyze it. There's not really much else there. .NET. So .NET's our newest SDK, and it has some interesting challenges in and of itself. It's like a more flexible, and I'm not going to say more sane because I don't want to upset anybody on the call, more flexible runtime from this perspective a little bit. So .NET does have coroutines built into the language, and they call them tasks, but they mix back and forth with the thread pool a lot. And they don't always tell you when they're going to. So .NET has this one big global static thread pool. You can't even customize it. It's a static class, just like a big global static thread pool. And they tell you, oh, run on that thread pool as needed. And some of the implicit asynchronous calls inside of .NET may be scheduled on that thread pool, because they allow us to create, and we have created, a custom task scheduler. And we've made a deterministic task scheduler that makes sure that if you do an await on a task or create a task using this scheduler, we will make sure it goes in a deterministic order. The problem is they don't always use the current scheduler. They'll use the system scheduler or the default scheduler, and they'll do that implicitly. And it's hard to know when that occurs. They can't really sandbox .NET well anymore. They used to could, and we'll get to that in another slide here in a minute. And their timer implementation uses the system timer, doesn't allow you to intercept it. So if you did a sleep, you can't intercept that. They have just merged an API that will make that easier, but we support some really old languages, or really old versions of .NET, so only newer versions get that done. So, and just one note, .NET is really young, it's still in alpha, so some of these things are still being researched. So the first approach is runtime tracing. We actually implement this today. Since it was so hard for us to know when a task would accidentally be scheduled on a thread we don't own non-deterministically, we put in a runtime hook. So they allow you to have this event listener that basically listens to all task scheduling. Unfortunately, it doesn't allow us to only listen to it in a certain case. So we listen to all tasks across the whole process. But it's a really quick thread local check for us to determine whether we're even inside of a workflow and then just discard it. So it actually doesn't hurt performance that much. But we will catch tasks that are scheduled from inside of a workflow onto the regular thread pool. This actually happens surprisingly a lot. I was using the data flow library, and it's somewhere deep in there. I opened a bug on .NET, deep in there, scheduled a task on the default scheduler, and would have broken determinism. Problem is, we only catch that at runtime. And that suspends the workflow. It fails the task. It is not necessarily the best. So while it's not that hard to write, it's a B for difficulty, it gets a B- for effectiveness because it's at runtime. And of course, it only catches threading issues, doesn't catch any state management issues. Static analysis is where .NET shines. Compared to all of the languages that we support, .NET developers and the .NET ecosystem support static analysis so much better than all of them. Built into all the IDEs, the tooling around it is very mature. Almost all frameworks provide that do these kind of things in .NET provide their own static analyzers. So we'll be obviously writing them too. We can catch illegal calls with them. Granted, they'll have to be transitively checked, and you can work around them with reflection like you can with all these. We'll have limited effectiveness on shared state mutation, but only limited. So it's a very good approach in general. So we get this B for difficulty just because I actually have to write it, but it's not that hard. And the effectiveness is an A-. It's going to be great. It's going to catch all sorts of issues. We just have to write it. And those things that we catch with the runtime tracer, we can know ahead of time certain calls that are known to use the default scheduler by default and catch those at compile time. So that's a win. There is another approach. So, .NET compiles down to CIL, and you could interpret it, and there have been interpreters out there, but there's not really many good ones that are full featured. So we can't really rely on one out there. So it would be a huge effort to write. And older versions of .NET back in the framework days, pre-core days, had app domains and code access security where it was like an insecure sandbox, but was still a sandbox. That has been done away with, so we can't rely on it. So this is an area of active research, but in general, probably not going to come out to be very fruitful. So now that we've gone through like the 5 common runtimes for our SDKs, let's talk about a couple of general approaches, because I always get asked about these. I'll be at an event or something, and I say, why don't you sandbox the entire OS? There are tools out there that'll sandbox the entire OS, and they're getting more and more popular. So Facebook released Hermit recently, which puts which replaces syscalls with deterministic equivalents and allows then deterministic replaying. The problem is that is so low level that it violates our rule from the 3 determinism violations that developers should be able to know when their alterations make a non-deterministic change. If the Go runtime is inside of there making a random call against an OS level seeded random to change up map ranging, you're not going to know that a Go standard library alteration that adds a new range map messes up the seed and then messes up other pieces of your code. Same type of deal with schedulers. These schedulers for coroutines that rely on thread pools or just threading themselves, it can be hard to know what minor alteration may alter the order of two threads started right at the same time. Even though they're deterministic for their same code, it is code alteration where this really burns. So if you don't have to worry about any code alteration and all your workflows result in completely new runs and never have, then this could actually work. Otherwise, since most users do actually alter their workflow, this gets a pretty bad difficulty because people have to run it in a container separately from their runtime anyways, and it's not that effective on the code change part. Another thing that everybody asks for is, why not WASM, right? And WebAssembly is deterministic. Yes, very much so. The problem that WASM has, at least self-hosted inside of these languages, and we'll get hosted in a minute, and I'm not going to cover each language's annoyance here. We'll have the slides available after the talk. But basically what happens is most of these runtimes, when they're compiled to WASM or run in WASM as interpreters for their code, like .NET and Python do, it has the same problem where you can't really tell that a slight alteration of your code will alter the coroutine order or alter a randomization, a seeded random order. So like for instance in Go, the way they build this inside of WASM, if you were to disassemble WASM, is that at the top of the table is a huge jump table, and that's how they support yielding. That's how they support preemption inside of functions. And you can't know that the scheduler, if you make an alteration, that the scheduler is going to pick another one to yield before you. So it is not predictable on code changes, has that same problem. However, if you don't care about code changes, then you're actually pretty good. The difficulty of this, and the reason that I have it as a C here, is that this is the self-interpreted WASM slide. We'll get to another one later. And it doesn't have good it doesn't have the same type of support in each language, and we have to write the host or reuse the host in each language. But it would be reasonably effective. So here's the verdicts. And I want to make sure I leave enough time here for questions. So I'll touch on a couple of other slides here in a minute, and then we'll be good. So Go. We already got a static analyzer, but other options are just not that doable. On the JVM, we need to write a static analyzer, but mostly there's not much else that we can do. In Node.js, we got a Sandbox. It's awesome. May write the static analyzer for the query handlers and update validators. Maybe not. We'll see. Python already got a Sandbox. Works reasonably well. Need a static analyzer. And basically, if you noticed, all of these that aren't really well sandboxed need a static analyzer. Same with .NET. We got runtime tracing. We need a static analyzer. Otherwise, most options for interpreting and things just aren't that usable for people that like to use their activities right alongside their workflows. Now, a couple of other additional things, and I'm going to hop past most of these, and we can discuss some in questions, or you can catch me on Slack. I'm everywhere. So first of all, replayers. You should be using a replayer. If you're doing any kind of workflow stuff, download your histories and run them through a second or third time just to confirm it's not deterministic. Everybody should be doing this in their CI. I can explain details on how to use it for anybody that wants. We have lots of docs about it. It is almost a must to ensure constantly well-running code, and it will help you when you make code alterations to feel confident that they're safe against your past executions. There is a possibility for a future that that the server could host the WASM. If you don't care about your activities running somewhere else and you just want to care about the workflow code, there's no reason we can't compile that to WASM and then run it in, or even have more of a like temporal specific workflow language that runs inside of the temporal server. There's a lot of value to this, but for now, a lot of people like their activities and their workflows to be married right there next to each other. But this is an active area of research and development in temporal, and definitely something that we are thinking about. And then as an interesting challenge to end up, because AI is all the rage, I gotta hit that SEO. We went to. I have to write all these static analyzers. Like our SDK team, we're all tasked with writing all these static analyzers and all these things coming up. But all these tools, or all these AI tools, and especially with ChatGPT and similar, are doing a good job at doing static analysis. Most of the news stories are about their code generation, but static analysis is where they also shine quite well. And you would have to have tailored models to do this well, but let's just go with GPT-4, state of the art, blah, blah, blah. So we basically gave it a prompt. I'm not going to read the prompt, but we basically said, we need the code to be deterministic by temporal standards. And just as a proof of concept, we dumped a bunch of code, but we threw a bunch of, we dumped a bunch of code and we said, is this deterministic? It said, yes. And then we made some non-deterministic changes and it immediately found them. Now GPT-4 found them. That doesn't mean that your favorite language model is going to find them. And GPT 3.5 didn't do that well. So there's still a big gap in the AI industry here. But it found right away that we threw asleep and we're doing logging inside of the workflow. So if you have access to GPT-4, use it to check your workflows. It might have wrong answers like ChatGPT often does. So you'll still have to curate the responses. It can be a good little sanity check just to kind of make sure. Unfortunately, with context size and other limitations, you can only check a little bit at a time, and it can't really do it transitively. But otherwise, it knows about temporal and understands it reasonably well. It'll still give some wrong answers here, so AI hyper beware. So just some quick notes on that. So yeah, feel free to use it. We're considering writing a tool that will do this. Whether it uses OpenAI or not is a little bit of a challenge because OpenAI is a little bit expensive for the GPT-4 use case, especially for constantly statically analyzing code. But as things are going so much faster, open source is catching up. There'll be surely an easily fine-tunable model that we'll be able to run here at Temporal, or that you could probably run, that will probably catch these types of mistakes. So at this point, I'm asking, and the team's asking, why are we going to spend a whole bunch of time handwriting static analyzers anymore? I'm skeptical. I don't want to spend a month toying with typed ASTs to get everything right, just to know when I could ask GPT in English. Some of these languages, though, like .NET, still have an analyzer framework that we need to stay within. But this is a very active area of research in Temporal, and if we can leverage AI to catch your workflow mistakes, we're gonna. And so we have a whole AI team working on this and think about this. So just like every other tech industry, we're looking into it also. There's also something we've been toying with, which is just basically fuzzing the workflow. We know all the possible ins and outs that can come, and deterministic code is great for fuzzing. And especially with like modern Go fuzzing being built into the language, especially path-based fuzzing, it's definitely an area of research and is something we very well may implement, but we have to do it for each language for the most part, because we can't go back and forth to a server. Fuzzer just needs to iterate much quicker than that. So we've toyed with a little bit of this. We have some plans around this, but not much there. So overall, that's how determinism works in our, let me clarify. The challenges of determinism in the different languages, runtimes that we have, some of our ideas for the future, and just in general, the cool problem that faces temporal engineers. So we're hiring because it is such a cool problem. Like it's the greatest job ever, right? To be able to toy with these language runtimes and get them to work the way you want. So feel free to get in touch in general. Like if you have an idea that's like, oh, well, Chad, have you seen this thing? I would love to hear it. We're public Slack, the forums, any way you want to get in touch, feel free. And like I said, we are hiring, and that's basically it.
Cool. Thanks everyone for your time. Thank you, Chad, for your time as well. And I hope that everyone has a great rest of the day.